презентацијата. Го минимизираме. Да, на англиски ќе зборува Томе, меѓутоа презентацијата ќе биде во рамките на сесијата која што се организира заеднички, значи од EuroCC проектот кој што е кај нас во Скопје, заедно со проектите, значи AI Factory, проектот од Словенија, исто така Томе ќе ги каже
AutoLLM-SI.
Така, значи тие се проектите кои што преку кои што всушност соработуваме со колегите од Словенија и всушност денес тие ќе презентираат накратко што работат, кои се најнапред, докаде напредокот во оваа област и потоа ќе имаме една кратка панел дискусија. Tome, the floor is yours. From now on, the presentation will be in English and also the discussion will be in English.
Thank you, Riz. So this workshop is actually, we are going to present some novel concepts that are going in automated machine learning and automated optimization. And at the end, you will see like there are a lot of projects actually that are funding like this kind of work. Some of them are coming from European projects, some of them are coming from national projects. Today, I'm going to talk about leveraging benchmarking data for automated optimization. This work which is going to be presented is mostly done by Anna and Georgina, Anna Nikolic and Georgina Cenik, but you will see like a lot of people who are working on similar topics. So what is the idea behind? We are going to talk about benchmarking because you already saw like benchmarking are pretty much famous, and especially in these large language models when you can see like there is a new model that beats some other like large language model, then different tasks, different metrics, and so on. And then we are going to talk about something that in optimization we want to call like learning for optimization. However, if you are working in machine learning, you need to talk about meta learning. And for example, if you have in the room like people who are doing only machine learning and only optimization, and if you say we are doing meta learning, the people from machine learning will not be happy because that meta learning is a concept that is actually learning from models from machine learning. And then if you are learning from raw data, which is coming from optimization, they want to call this like learning for optimization. And it's pretty much big discussion about these two communities, which are fighting like what is like the correct term. So then we are going to talk about something like at the end, if I have time, I'm going to talk about algorithm footprints. But first I'm going to show you like what are the steps we need to care in order to do some fair benchmarking. So what is the idea? When we talk about optimization, we typically have like single objective optimization, and in single objective optimization, we would like to find like a single global optimum, which we have in the function. And also we can talk about a lot of multi-objective optimization. And when we are talking about multi-objective optimization, we don't have one solution, but we have like a set of solutions which are non-dominated, and actually they are forming like the Pareto front. If we talk about theory, we have the Pareto front. Typically, we are using like evolutionary algorithms to find like approximation of the Pareto front. So we are typically empirically, we are obtaining like the approximation set. So what is the idea? Think about large language model, and then you need like the large language model to evaluate a large language model. You can evaluate a large language model based on accuracy, right? But also you can think about bias, or you can think about like how many CO like the green emission metric. So in order like to find like the best model which is suitable for you, you can do like such kind of Pareto optimization, like multi-objective optimization, and then to select the best model which is going like to happen. Actually, after me, Anna Georgievic is going to present a really nice study for large language model to see actually how we can change the ranking based on your suitable scenario. So today I'm going just to show you some examples in single objective optimization. It's like the most easy. We have a lot of studies that also like have been done for multi-objective optimization, but it's a more complex like mathematical object. So I'm not going like to talk about today. And then maybe like just for illustration, when we think about like this benchmarking and learning for optimization, typically what we are interested is actually which problems to be selected. And we have like this problem also in machine learning scenario, right? For example, you have a new model and you need to evaluate your model. And then typically what we are doing, we are going to OpenML, or we are going to some famous benchmark data sets, and we are evaluating like our model to against the state-of-the-art models using all those data sets. But then we can see that this is actually not correct, like way how we can do this. And then the idea is like which algorithms to be selected, how we know like what are like the state-of-the-art algorithms. If we are including in our studies only like the algorithms which are beaten by our novel algorithm, or actually we need like to include all possible state-of-the-art algorithms. And then we need, once we collected the data, what we need to do is actually with statistical analysis, we need to apply. So those are actually the main questions that need to be addressed, but typically how we are working. When you run like an optimization algorithm to a given problem, what we are typically doing, we are collecting a lot of data from the evaluation, right? So actually we have the trace, the entire trajectory of the algorithm until like the convergence, but also we can have end performance, different performance metric. And typically when we are doing like the running of the algorithm, we have some single objective function that can be a sphere function, Rosenberg function, or even like function which is coming like from industry. And then we have like all these like things. So if we have a problem or function that should be optimized, we can find its characteristics. So we can think about convexity, multimodality. We can also do some information, like information theory features. We can find some near neighbors features. So actually we call them some meta features or high level features to explain like the problem. And then what is the idea? If we collect all this information which is happening when you are running the algorithm, you can take all this data and then you can put this data in an ontology. So now we are talking about semantic web. So this option ontology is actually developed to do like benchmarking optimization ontology. It has a performance data, characteristics of single objective optimization problem instances. It includes like different benchmark suites. We have the Nevergrad, which is actually the benchmark suite from Meta. We have also like COCO benchmark dataset, CEC dataset. So actually, if you go like to those conferences, Gecko and IEEE CEC, all this data which is collected like during 10 years of competition, so the state of the art, all this data is available in this ontology and it's actually searchable by Sparkle. Then what is really important, if you think about we have these all competitions together. What we showed before like 4 years, that actually the algorithm, which mean like 2022, it's actually not so good as the algorithm that was published 2012. So 10 years in the community was not done any progress. And people are inventing novel algorithms every year. And we have a winner. Why? Because actually they have never compared like the results with the winner from the previous year, or actually from 2 years before like the competition. So now what is really interested for us is actually, and there are a ton of algorithms, like a lot of algorithms. What we are doing currently is actually, we are doing selector, and then you will see like some details there. When we talk about selector, is actually what we said first, which optimization problem should be analyzed in the benchmark dataset. If you think about machine learning perspective, you need to think about, okay, now I have like, I don't know, 50 datasets. So for example, in univariate classification for time series analysis, you have 108 datasets which are publicly available under one repository. And then what is the idea? Do we need like to use all of them to compare our models, which is typically done at ECML, ICML. So actually those are like the standard benchmarks. And then the idea is, do we need to include all datasets, or we need only to select few of them in order to have fair benchmarking? So this selector, what is doing in optimization, but also it has a lot of application also for time series, for large language model prompts and so on. The idea is actually how we can select on which problem instances we need to compare our algorithms. Then if we solve the problem, which problems to be selected, which algorithms I need to compare, what are the state-of-the-art algorithms, right? We typically include deep neural networks, some transformers. I don't know. In optimization, we use covariance matrix adaptation evolutionary strategy against like genetic algorithm, differential evolution. But how we can include the state-of-the-arts? So let's do this data-driven, because we don't know which are state-of-the-art algorithms. Can we actually select which are the state-of-the-art algorithms before we include in our analysis? So actually, the entire experimental design, what we are doing, we are automating the process without like human to decide what it needs to be done there. Then I'm not going to talk about statistical analysis. We have done a lot of approaches there. And what is typically really nice is the algorithm footprint. And this is done with the University of Melbourne. I don't know if you heard about instance space analysis, which is pretty much popular in machine learning. The idea is, can we detect on which problem instance our algorithm works and what are the reasons that provides like this kind of behavior? So it's not about, I mean, for example, if you think about machine learning perspective, think about you have a lot of test instances, right? And at the end, we are just providing like the average accuracy or some F1 or recall or precision. We are not interested in this aggregated measure in automated machine learning. What we are interested is actually, can I say what are the reasons for each instance to have like a good prediction from the test data? So we don't want to aggregate, because when we are aggregating, when we have, for example, a regression task, we can have for few instances really big errors, and then if we do aggregation, right, if we don't show the box plot, then actually we have really big error. So the idea is, let's explain what is happening on each problem instance in our like test data. So typically when you talk about benchmarking, these are like what I said, the three questions. We have selection of problem portfolio, selection of an algorithm portfolio, and then we are collecting the data, and at the end we do some tests, ANOVA, Friedman, whatever t-tests, like Mann-Whitney tests. So this is like how a typical benchmarking scenario is done. But actually, this is like the statistical comparison. Probably I speak a lot about this like in previous years, so we are not doing anymore. We are still using it for some papers, but actually we don't do like a lot of statistical analysis. What is the idea? When I spoke about like those optimization algorithms, and typically this is currently also the situation with large language models, there is like a paper which said like metaphor-based algorithms, elephant in the room. So actually we have so many algorithms. Every day we have a new bio-inspired algorithm, and then we typically don't know if this algorithm is better than some state-of-the-art algorithms. And currently, what are a lot of publications are actually showing that a new algorithm, which is actually published this year, is the same algorithm as algorithm published 2010. And there are a lot of such kind of papers which are going, and the entire community made this like editorial paper. We said, okay, we need to stop doing this, because, okay, we can have like publications. Publications are important in academia to go in the next scientific title, but let's not do this, because actually we don't need to do, we need to make something like to be transparent and trustworthy benchmarking. So what we want to do is now, okay, if you want to contribute to the science in this community, you need to explain what are the benefits of your algorithm, even if the benefits are happening only on 2 or 1 problem function. So we need to confront the elephant in the room. So what we are doing, instead of doing like all these kind of things, statistics, we are doing like the entire benchmarking data. We are collecting the data, but instead of we have the problems, we have the algorithms, we are running the algorithms on the problems, and then what we do, we use a lot of features. So we have features that are describing the characteristics of the functions. We have features which are describing the algorithm internal state variables. And then when I said, okay, we are running an algorithm, and then if you collect the trace, the log file, right, of the algorithm, how it's running until convergence, you get a lot of raw data about the entire trajectory. So we have features which can be actually extracted by the trajectory of the problem algorithm interaction. And now you can do like explanation on these different kind of levels. So you can use all these kind of features in different kind of applications. And now the question is, okay, I would like to do an algorithm selector. What is an algorithm selector? Typically, it's a supervised machine learning model. It can be any learning approach behind. And then the idea is, if I have like, think about, you have 50 algorithms, and then you have a lot of problems, and then a new industrial problem is coming. The idea is, do you need to run all of them and find empirically which one is the better? But when you have an algorithm selector, the idea is you have a machine learning model that will tell you which of these 50 algorithms is the best for the new problem. And then actually you can run only this optimization algorithm. Then if you think about algorithm selector, you can model this from machine learning perspective, like regression task, classification task, pairwise regression, pairwise classification, multi-class classification, multi-label classification. So it depends like what kind of data. And then when you have like the learning task, you can use like different kinds of modeling approaches, right? For example, we tested random forest, XGBoost. Probably you heard about TAP-PFN, like the biggest startup in Europe now by Frankfurter. And then we have this FTT transformer, which are actually transformer for doing like regression. So actually you can test all these different models in different learning applications. And then you can see like if there is some benefit to use transformers, or actually probably you saw those on Instagram. I have a data classification task, and then the data scientist is putting like simple oil, like, okay, let's do transformer. when this task can be actually solved by a random forest or decision tree. So now all people want to do transformers or large language models because it's fancy, but actually you can work with some simple mode. Okay, I'm not going to talk about the features. There is a really nice survey paper. There is also a tutorial from the AutoML conference. Also this year, like in New York in September, there will be a tutorial about this. You can go to this QR code and then you can find. Maybe just to tell you that when we think about problem features, why the problem features are important. The problem features are important when you want to analyze only the function. So now you don't have interaction with some algorithm, but you want to say, I would like to have diverse problem functions with diverse properties. Then when you think about algorithms, these features are important when you think about from the perspective how to select the algorithms. But if you want to do some hyperparameter optimization, or for example, think about you start with differential evolution algorithm, but during the run, you would like to switch to particle swarm optimization. So you would like to make hybrid models. And then based where you're located in the search space, then you need to use the trajectory features because you need to learn exactly from the search space where this algorithm actually stopped or what is like the next where to go. So the problem features, just to tell you, you have functions. What are you doing? You can use some sampling techniques, uniform sampling, Latin hypercube sampling, Sobel sampling. So actually you are sampling from the entire like decision space, you are evaluating the function, and then you can calculate from these metrics like a lot of features. Then when we think about algorithm features, sorry, just to, okay, these are the problem features. The algorithm features we have like based on source code. This is something which is actually proposed by one group from New York. But the idea is they are too weak. Think about like this. I'm not a good programmer. And then I can implement some algorithm that is working. But then I can give like the same algorithm to be implemented by Rista. And then we have completely different programming style, or by Anna. Like Anna is really good, like software engineer. And then what we can do, if you analyze my code with NLP embeddings, Rista code and Anna code, and it's the same code, probably like the features will be completely different. And it's the same algorithm. So you need to think about what is the application like behind why you are doing this. Then we have based on performance, we have based on Shapley values, which are pretty much, and Shapley values are actually the first time in the community were done by Rista Trajanov. And this is like really, this was the diploma thesis before 3 years, I think, or 4 years. I cannot remember, but these papers are really, really like highly cited by the community and were the first attempt like doing this. And then we have via knowledge graph. So what I said to you is actually we represent the entire data as ontology, right? And then like all those instances are forming like the knowledge base, and each knowledge base in an ontology can be treated as a knowledge graph. And then we can do a lot of graph-based techniques, graph neural networks and everything to learn like what is the best algorithm. These are the problem algorithm trajectory features. What is the difference? If you remember about the function, I said, okay, we are sampling from the decision space of the functions. If we do like a trajectory functions, we are not sampling. We are just looking into solutions which are visited by the algorithm. For example, the population, which is formed by some population-based optimization algorithm. And then we are extracting the features using like the observed solution from the trajectory. Now I will show you only two applications. One is selection of representative learning data, what I said to you. Think about like this. We took 3 algorithms from Nevergrad. This is Facebook. At that time was Facebook, but now it's Meta. And then we use those 5 different benchmark suits. And then we run the algorithms, real space particle swarm optimization, covariance matrix adaptation, evolutionary strategy, and differential evolution. And we do simply Friedman test. If there is a difference between the performance of those algorithms, and maybe just to tell you, Coco has like 24 problems. CIIT 2013 probably 28, 29, every year like they are changing a little bit the functions. And then look what is happening. If you think about BBOB or the Coco, we can see that there is a difference between the particle swarm optimization and differential evolution, and particle swarm optimization and covariance matrix adaptation. And because we are doing one-sided post-hoc statistical testing, it seems that the particle swarm optimization is the best algorithm. Now look what is happening at CIIT 2013. All of them are the same. There is no statistical significant difference. 2014, again, the same. if you go to 2015, differential evolution is the best. And think about on Coco, PCO is the best. And then if you go like 2070, it will come again that particle swarm optimization is the best. And if we collect all functions together, we have that the particle swarm optimization is the best. What to publish in my paper? Now the question, right? Because actually I can publish everything. I have all the outcomes, only I don't have the outcomes where the covariance matrix adaptation wins. So this is really a problem because actually, and this is a problem, for example, I will tell you later, like from machine learning perspective. So what we have done, we use some most commonly used features, exploratory landscape analysis features, and then we calculate 64 features that describe this problem. So think about now each problem is actually a vector with 64 features. And then when we have these data, these are the number of problems we analyze in 10 dimensions. We use two different approaches. One of them is actually, we group them all together. Now they are represented with the same meta features. So if you think about NLP, they are in the same embedding space, right? And then what we can do a clustering. And then one approach will be, if I have all possible clusters, I can uniformly sample the same number of functions from each cluster, because what I want to have is to have a feature space functions which are close to uniform distribution in the feature space. And then the other approach is actually, instead of doing this, let's connect them as a graph on this way that each node in the graph is actually a problem function, and they are connected if their cosine similarity or Chebyshev or whatever similarity you want to have is actually exceeds some threshold. And then we can connect them. Once I connect them as a graph on this way, I can do a lot of discrete math on the top. So I can use dominating set, maximal independence set. There are a lot of algorithms that exist. So I'm even not an expert there. But actually I can do this and then I can repeat and I can get only like the halves from each component, which represent the entire space. So why I'm doing this? Because I don't want to have overrepresented spaces in the feature space. And now maybe one thing, I got before 1 week I was on this panel in Slovenia with this Ministry of Digital Transformation and everything. And I got the questions about bias and data and everything. So I always answer like this. If you are doing academia, you need to care about this. If you are doing like an industry, if I have overrepresented spaces and all the revenue in the company is coming from clients which are in the overrepresented space, I don't need to care about like this representativeness of data, and I will overfeed the model only there because this is what makes money and actually run my business. But if you are doing like academia, if we need to say, for example, we saw in the previous presentation, better large language model, better, but there is a lot of data leakage there. Like there is a lot of information leakage, not transparent. So we don't know what is happening there. Even, for example, in Hugging Face, we have the model cards, right? And those model cards should have information, what is the training data. And there is a new study from Stanford, which show actually that this information is actually missing. No one has like this information reported. So in our case, what we are doing, think about, we have the clustering. We can cluster on 21 and 26 clusters. And then what is the idea? I can just use the centroid of the clusters as a representative function. And then I can do like this, and then I got like this result. So it seems like that only a difference between covariance matrix adaptation and particle swarm optimization. And then I can do also 26 clusters based on the silhouette score, the same information. And then we can say, okay, but let's give more flexibility. Why using only centroid when we can do this sensitivity analysis and we can define like some epsilon neighborhood, a sphere around the centroid, and if function is in this like sphere, in this different epsilon neighborhood, you can still include it, right? A little bit more flexible. We repeated them, and then we have like, we can repeat it 50 times because 15 is actually the number of instances in the smaller cluster. We don't want just the repetition to have. Look in these results, again, the same results. So, for example, differential evolution and covariance matrix adaptation, 14 out of 15, there is no difference. So there is like a bootstrapping doing like a permutation test in statistics. And then if I do like doing like a graph and selecting from the graph, and you can see like these different thresholds of creating the graph, 0.9, 0.95, 0.97, and then using different methods. And then we can bootstrap this because those algorithms are again stochastic in nature. So if you have a component, there is no guarantee that the same hub will be sampled all the times. You can see, like, for example, that we got the same results. So actually there is a lot of robustness. So you are not showing something like which is happening by a chance, which is in favor of your algorithm. But what are you doing is actually you can say, oh, my results are really robust. Like, I really know that my algorithm or my optimization algorithm is the best one. And then just to show like the generalization, not the reviewers, not to tell us that this is only valid for one combination we select a lot of combinations. And then you can see like the first columns, like how these results differ. And then you can see when we use the clustering approach, dominating set and maximum independent set, you can see how the results are actually consistent. And why this is important, because we have done like another study. We took like all these univariate time series classification models and all 2022 and all papers that were publishing at ICML, NeuroIPS, and ECML PKDD. All these famous group reported like the best results, superior results in time series. We took all those algorithms, all data collected. They benchmark on 108 data sets. We showed that from this 108 data set, 73 are covering the same space. If your algorithm is hyperparameter tuned there, it's the best in these 73 algorithms. And then the other data sets, 30 data sets, are not important because when you are doing Friedman statistics, you are just averaging ranking and you are getting like as the first one. And then we said, okay, let's now do like again everything what people have done in the last year on those competencies. Let's see what is the best algorithm. We select uniformly across the data set space, and then we just report like what are the results. So this is actually one part which we need to care when we are doing automated machine learning. Why? Because actually we are caring about the representativeness in the space and what are like, maybe just to tell you, I don't have this on slides. Some of you maybe are interested in reinforcement learning, right? So when reinforcement learning is using for algorithm configuration to find the best parameters, for example, for combinatorial optimization or some continuous optimization algorithm, typically what people have done, they're training agents on each problem separately and evaluate them. But then we show that if you smartly select on which problem you need actually to train the agents, even you are not covering the entire problems, because some problems are similar in characteristics, you can have much more generalizability on the test data. Okay, so this is the automated algorithm selection. Now, what we have done is actually we think about only the first part, the problem portfolio. And this is like the first thing I need to do in order to have experimental data design before I do something, before I do some other machine learning task. Now, what is really important is also the algorithm portfolio. Because if I have this really nice, I will reduce the bias there. Then I can do this really nice, easy transformers, whatever, like I can find a model that works like nice. So what is really important is how to do like this algorithm portfolio smartly. So what we have done here, if I go back, I said, okay, we have problem features, we have trajectory features, and we have algorithm features. So now think about here that we have like, this was published at AutoML in 2023. And what we have done, we have this SHEP meta representation for the algorithms, and we have something performance to back. So I'm not going to explain those features. If you have questions, like we can talk later. But actually, here you have the same algorithms, which are represented only with different features. And then what is the idea? We have around 576 differential evolution algorithms and 326 different modular CMA. So these are algorithms that have like different parameters, and with this they have like different behavior, right? And now the question was, can we select the best hyperparameters that should be used for a given function? And then we said we have a pool of 324. Which one is the best? I don't want this manually to see like the average scores, but I would like actually to have a model in advance to give me like what are the best hyperparameters. And then if you go like there, we represented them like this. And then again, this is a graph, right? Similar to what we have done with the problems, only we use like our nodes now are algorithms and connected together. So the same approach here. And the idea was, okay, we have them, let's use maximum independent set or dominant set. And you have something like this. Why? Because actually what we can do is we can have, instead of 324, we can have a representative configuration across the space, and we can select only from 10 algorithms or 5 configurations. So we want to have a diversity in the algorithm space. We would like to have complementary, because some algorithm is good for a sphere function, the other configuration is good like for the Rosenberg function. And then this is a really nice, because actually it has a decomposition of error of an algorithm selector, which is a machine learning model trained to give you like the best configuration. And our idea was, okay, if we use the entire portfolio of 324 algorithms, and if we use our portfolio, which is actually 10 algorithms, do we have a better loss in the algorithm selector, which is a meta model? And then you can see, for example, this diagonal, which is going from 2 to 2, with these 2 points, like this is 2, 0, and then we have 0, 2. What is the idea? This is actually our baseline. The other thing, what is really important, how people are doing this in hyperparameter tuning. You have this greedy accuracy and greedy per function, which are actually the circle, and this like, I don't know, the last one, like a star. So these are like the best configuration done by human. And then you can see that we can find a lot of portfolio which provides like much more better results which are done. So how we are decomposing this kind of error? So for example, on the x-axis, we have the best possible loss of the portfolio, the difference between the portfolio virtual best solver and the virtual best solver of the 324. And on the y-axis, we have like the difference in performance between the algorithm it selects and the virtual best solver only from the portfolio that was selected by our algorithm. And then if you see in the errors, we can see like we can find portfolios that has like a really smaller error than even like the baseline, the standard, which is done by the humans. So we can automate this kind of process. And why this is important? Now, for example, even like in LLM, right? People are doing like this orchestration, whatever, based on the prompt. The LLM is switching between one model and the other model, and all these kind of things. So these kind of things are important, because if you think like of a meta model and how this approach, for example, deep search is fighting with OpenAI, how this is done. So what is like these meta models, how they work? If we really want to benchmark them, actually we need to find a portfolio of LLMs that are the best for them. And how we can do this? Actually, we can use this kind of approach to select the LLMs, and then we can start using their algorithm. So if you have a new approach for algorithm selection you are developing, and you want to show that your new meta learning approach is the best, that all other meta learning approaches that exist, then you need to care about this, like to select the proper algorithm portfolio, because selecting a proper algorithm portfolio will give you like really nice results. Okay, these are the take-home messages. You should use approaches to understand what are the strengths and weaknesses of new algorithm instead of looking into its average performance only. So you need to have like this fair experimental design. And maybe, okay, this is the team. Gina, Anna, I need to apologize. It's an old slide. Anna Kostovska is already a doctor. It's not a PhD candidate. Then Jandrola, Anna is here with us. She's going to present some nice results with LLM ranking, and me. And this is a huge thanks to our external collaborators from Aachen University, Anja, Diderik. Diderik is currently at Sorbonne doing a postdoc from March 1st, and Carola from Sorbonne University. Now, this is like the funding that allows us to do like this kind of research. We have the Mr. Beck previous and response. Now we have active the auto, which is a national funding, how to do automated optimization. We are part from the biggest national AI project, AI Gravity, like similar to ERC, which is AI for Science. And then we have like support from this Horizon Europe project. We have the ERA Chair, which is active from March 1st for the next 5 years. We have one postdoc position open if someone is interested in this, but it needs to you need to finish a PhD. It's a Marie Curie postdocs. So these are like the really nice salary without taxes. Then we have the Horizon Europe Slovenian AI Factory, which are we are really happy that our group was invited and pretty much contribute to the AI service part. So this is like for 3 years, and probably it will become a national infrastructure in the next 20 years. And Anna will tell you more, like this is her postdoctoral fellowship, which is excellent in science. Marie Curie Skladovska action, which is AutoLLMSelect. And maybe just to tell you, Anna wants this, and the application was ranked like 99.8 out of 100 points. So actually, this was like pretty really nice results. It starts in June 1st, but Anna will show you like some preliminary results, which are actually going to do. I know that a lot of people here already know, and with a lot of you already actually talk about this. This is like the AutoLearn. Slovenia is really nice place. We have, it's not all 3 PhD position. It's only 1 position which is left, because actually 1 student from Poland and 1 student from Belgium already joined the group. We have also 2 postdoc positions, so people who are doing PhD here, like if you plan to finish till next year, June, you are more than welcome to join our group. And also, as I said, we have a Marie Curie in quantum optimization if someone is interested. So this is another position. If someone is interested, just write on this email, follow us on LinkedIn, and Ljubljana is a really nice place to be. And there are a lot of money for traveling. Whenever you want to go, you just decide and then you go. Because Anna knows, like our group, you sold them all here, but now I believe that from May 1st, the first time I will solve them will be actually September 1st, because they are going around the world. Okay, that's everything from me. If you have some questions, feel free to ask. If not, like Anna can show you some really nice LLM results.
Okay, thank you for your interesting presentation with a lot of information that covers your work for a long period of time. So, do we have any questions or discussions before we proceed onward?
One question.
Yeah.
At the beginning, you mentioned, well, I'm not into this, but it's meta learning, but you didn't mention it.
Actually, here is where is happening.
All of this is some of this.
These are the errors.
Yeah.
These are the errors of meta learning models. Like, so what we are typically doing, we have like those features, right? Here we calculate the features, we have the algorithms, and then what typically we are doing, we are training a regression model or classification. Regression is the best option if we can from all the results we got now. So what we are trying to do based on the features, we would like to predict the performance of the algorithm. There is like a really nice study which is going to be presented this year at Gecko. The idea is like, if you think about this ontology, right? So all these interaction, algorithm, problem, high-level features, and everything can be modeled as a graph. And then think about, now I'm talking a lot about configuration, different parameters, right? But I cannot evaluate all of them. I can make like a combination of parameters which I haven't evaluated. I can put in the graph, and then I can use a graph neural networks, graph sage, self-attention, just to predict what will be the performance, to know if this will be like good to run or it's completely not too good to run. So actually, when we have those features, now I present only these 2 parts before doing, but actually when we have these 2 parts solved, we have the features, we are just linking them there with the meta model.
Other questions?
This is more like academic discussions. I was thinking, because this problem is like we have multiple models and we are trying to choose from them somehow. What do you think? Can we apply some, let's say, new stuff from agents and try to put them more like live, so the models will let's say behave like autonomous agent, and then try to negotiate and find out what is the best for the model, and see if they come out with some solution without us writing.
Yeah, so there are 2 parts maybe on this. It was not presented as agents, but how actually different algorithms are communicating what I said. Now I always talk about, okay, I have a problem, I run an algorithm, I collect data, right? But then think about like this. I'm in industry. I want to solve the problem. I don't know with which algorithm to start. I can start with random search. But I will give the random search, for example, 10 iterations. And then here I will finish. And then the idea is like this information where I'm now. Do I need to continue with random search? Do I need to go to differential evolution or to particle swarm optimization? So they are communicating. And if I need to go, with what kind of information I should start the algorithm. So this is a kind of agents. We have two publications published on this topic, 2022 and 2023. One is IEEE CEC, the other is IEEE, the other is PPSM. I don't know, parallel problem solving from nature. And there is the idea was really nice because we always think about these interactions, right? But then when you are running the algorithms are also changing some, for example, think about neural network, learning rate, right? And all these kind of things. So we can do a lot of time series features like TC Fresh, Catch-22, or whatever you want. And then you can combine them. So we have something like this that is already going up. We have two publications. There is something new I'm organizing with MIT and Leiden this year at Gecko. And yesterday we decided which papers are accepted. It's large language models and agents for evolutionary algorithms, how to design like automated everything, not to think about this is algorithm, these are, but actually you have everything and then you would like something automatically to be designed. Now, there are some nice works. Some of them are pretty much simple, which are give me a particle swarm optimization prompt code and run it like this, which I don't support. But there are also like a really, really nice papers which are coming on in this way. The third thing about this topic is Carola. She got ERC Consolidator grant. So actually she is doing like such kind of fancy things. So we have like the data. And what we are trying to do there is to build like a foundation model for tabular data, not to have like any more optimization algorithm, but actually the optimization to be replaced by learning from machine learning perspective. So we don't care about, for example, from genetic algorithm, if I'm going to have a crossover mutation or what is the population size, so these kind of things. But because we have for all these algorithms on a lot of problems, even artificial problems, the data, what we are trying to do is the foundation models for tabular data. And think about when I'm talking about this foundation model for tabular data, I'm not talking about Claude, ChatGPT, LLM. There's one really nice paper in the student session yesterday. I don't want to say because I read the paper, which are doing tabular data, but with these LLMs, what is the idea? If you have tabular data, then for example, you need to try TAP PFN, which is by Frank Hutter, or you should try like Kumo by Yuri Leskovets. So they have only numerical features, so it's not suitable. People are they're fighting with this LLM and everything like textual data, but there are really big initiatives in Europe and also like in United States that they want to do foundation models, but only for tabular data, relational databases that have only numerical features.
Yeah, maybe that's good. Because for time series, they have done that, and there are a couple of foundation models which are quite good, but probably time series is tabular data in general.
And this like TAP PFN, they first have done like really nice, it's a Nature publication, actually, that comes before 1 month. This TAP PFN is done like on classification task, then they have done also to work for regression, and now they just extended this to time series. What is really nice because they have done it as a startup, and people from the bank, they don't have data science knowledge to use them, right? And how to use all these models. They even implemented this as Google Sheet plugin. So actually you can plug and then you can analyze all these kinds of data. There are a lot of initiatives, even University of Tübingen. If someone is interested in these topics, there will be from June 10th until June 13th, a really nice course organized in University of Tübingen in Germany. Really, I can share like the invitation if someone wants to join. But the main focus is foundation models for tabular data.
Is there an online opportunity to?
I think online it's not an option, but yeah, there is like it's a really, really nice place to be. Okay.
Do we have further discussions? One question about this automated evaluation.
Yeah.
How automated is it? Is it this data sets? Do you need to tune the input for the evaluation, or everything is very well structured, very well defined? The algorithms the data sets, everything once?
That's a nice question because I think if I remember in 2018, you have one paper at CIIT when I came to you, and then I said to you like that this is like really promising something. It was about genetic algorithm and that you need to provide a modular framework. I still remember like that paper. But the idea is like this. We did this option ontology, and now everything is structured, right? And the problem with the ontology is that you need to put a lot of effort to convince the community to start using the ontology. So what we were doing, like for 2 years, we were going on all these workshops and everything, and then we have a big support like from these famous European labs like Frankfurt, Nevergrad, Meta, from Facebook. For example, Meta said, okay, we are going to use optional ontology. And now when Facebook said that we are going, all people start using it. When we think about like this, when we think about algorithms to collect data, it's really important like to have like this all possible different combination to write hyperparameters. There is like really nice IOH analyzer and IOH profiler by Sorbonne, Meta, and Leiden. Pretty much easy to use. So this is how people from the community are using, and they are generating a lot of data. So now pretty much in the last 3 years, I can say that a lot of things are really nice standardized. So even people that don't have technical experience with the tutorials which are provided and demo, they can run all these kind of things.
Because you mentioned 500 data set, or I don't know how you remember the numbers, but
Because we use the same data for a lot of data. No, these are So, but this is like the idea. And then you collect a lot of data and doing a lot of meta learning. And currently, what we are also probably the OpenML initiative. So we are working a lot with this Joaquin from Eindhoven, all this OpenML data. Anna will tell you more. Like I don't want to tell you other things about LLM. Okay. So Anna.
Now we can proceed. We can proceed with your presentation. The next presenter is Anna Đorđević, who is she is a postdoc at Jozef Stefan Institute. She took her PhD here in Skopje, and now she is going to present her work together that she has done together with Tome. Anna, the floor is yours.
Thank you. So here we can start with the broader scope of our work. So this is the project that Tome mentioned, the Marie Curie project that was recently accepted for funding, titled AutoLLMSelect, Framework for Robust and Explainable Automated Large Language Model Selection. So several details about the project. It was accepted as part of the Horizon Europe program, Marie Curie Actions Postdoctoral Fellowship. The duration is 2 years, so we are planning to start it on 1st of June until the 31st of May to 2027. So the host institution is the Jozef Stefan Institute, the Computer Systems Department, and the associated partner that supports us is the University of Freiburg, Germany. So what is the motivation for this work? First of all, a large language model selection for specific use case is an open problem and non-trivial problem because different LLMs have different capabilities, performance and different machine learning tasks. We have several popular benchmarking platforms like OpenLLM Leaderboard or Helm from Stanford. However, there we can just see a large number of LLMs, for example, more than 4,000, I think, currently in OpenLLM Leaderboard, and just their performance across different datasets. But the open problem is how to actually combine those based on your interest in order to select the one LLM, and those criteria may not be just performance metric, but other non-performance criteria, like, for example, effectiveness, hardware resources usage, or parameter size, environmental impact, and so on. Therefore, so they're often conflicting. So in case of LLMs, we claim that the traditional algorithm selection process for a specific use case is actually impractical, because evaluating a large LLM portfolio results in high computational cost, and that then translates into negative environmental impact. Namely, you cannot select a portfolio, I don't know, or 10 or 20 LLMs and evaluate them all, because also you can have cost involved with that. And multiple evaluation scenarios may be required just to evaluate a single LLM, because we have different prompting strategies that may be considered. So the open problem that we try to address with this project is from the multitude of available large language models and their fine-tuned versions, how to select one to use on a supervised machine learning problem without having to evaluate large portfolio of LLMs on the labeled problem-specific dataset. Namely, we want to train meta models that can be used to predict LLM's performance, in which would be involved with lower computational cost than having to compare all different LLMs on the dataset. The main objective: develop a robust and explainable and evolving framework for selecting the most appropriate LLMs for use on a previously unseen general domain or domain-specific dataset without having to evaluate large portfolio of LLMs on dataset. We plan to develop proof of concept on a selected LLM portfolio, dataset portfolio, and performance metric. And we will develop the framework to be easily extendable, both by our site and the community, so it can be, so it can evolve further in future. The strategic impact of the project, as I mentioned, reduce costs, to reduce financial costs and energy consumptions from comparing a large set of LLMs on every single data set, reduced effort by selecting an appropriate LLM, even if it has to be fine-tuned, the fine-tuning time would be significantly shorter than selecting a suboptimal one. And enhanced reusability. We want to advocate thorough evaluation and reuse of already available LLMs before deciding to train or fine-tune new ones. So how do we plan to realize that? First, by starting with comprehensive benchmarking. So large portfolio data set in 2025, but we'll see more. And to publish robust and transparent complementary analysis of that portfolio of data set, to find their similarities and differences using various text representation methods, and to compare them in common vector space. To see if some data sets overlap, how is that vector space actually covered. The second objective is the automated LLM selection, to develop a framework which allows the prediction of LLM performance measured by a specific metric on a previously unseen data set. And of course, so those could be a smaller meta models tied to an LLM data set and performance metric that would be easily extendable in the future. And the third objective, proof of concept and actual applicability of the concept. We want to evaluate the framework capacity to actually select an appropriate LLM that would be able to solve a problem with associating indicator with sustainable development goals from the United Nations Agenda for Sustainable Development, a problem I was working in my PhD. So we want to go a step further. We want to see whether those meta models would actually guide us in the right direction, would tell us which LLM is appropriate to solve that problem. So that completes my presentation on the project.
Maybe Anna, maybe we can say like to the young generation that if you want to do postdoc somewhere, the best option that you can do is actually to apply. This is your own money. So actually, you are applying for such kind of project. It's a little bit difficult to get it, but the idea is like this is your own money, so you can do whatever you want to do. So you just need to find a host institution. It should be like different institution where you didn't finish the PhD. It should be abroad, and this is like the salary. It's not going under taxes. This is like because you get like European salary. It's the excellency signed by Europe. Also, if you have a family, like you got costs for the family to move there. So this is like the best postdoc position if you can think about like to move somewhere if you want to do. If you want to go to some other projects, you will have like tasks from the project that you don't want to complete, but you need to complete because you are paid by the project. This is typically how it works in academia. And everyone, like, you can also text Anna if you have questions, because like this was a really nice journey, like, and when the project was selected, we were really happy.
That was that as Tome said, is a really nice grant from European Commission.
And maybe Anna already said about the University of Freiburg, right? Because actually what you need to do, you need to find a host institution, and then you need to move for a few months from the host institution. She's going like to University of Freiburg, so actually she's working with Frank Hutter, who is doing like TAPIEP and all these like models. So she will join like their group for some few months to do the research together.
Okay, thank you, Anna. Question, discussion?
Question, do you have any, I don't know, results from like preliminary this project, or
No,
I mean, I know that you're starting it, but since Thomas said that
so she will
you
present.
have, okay.
She will present now. This was actually
Okay, yeah.
But
Yeah.
this is just like a plan. Post.
Yes, I'm going to take code for you.
She has a presentation.
this is much more like just like all possible opportunities that
Oh,
you can do in future.
Yes, this is a small part of the whole project, but some preliminary, very interesting results we got. So we titled the presentation Robust and Interpretable Large Language Model Ranking based on user preferences. It is a joint work between myself, Anna Nikolic from our team, and our supervisors, Professor Barbara Korušić and Tome Eftimov. So I will start with the motivation for this work and research questions. So, as I already mentioned, the motivation, the increasing number of large language models which are available today, all having different capabilities, and those capabilities being evaluated on different data sets with different performance metric. So we rarely have the case when we have to decide only based on one data set and one performance metric. We usually have to combine multiple of them. We also may need to combine performance metrics with non-performance criteria such as parameter size or carbon dioxide emissions, some kind of environmental impact with those performance metrics, and they can be conflicting. So if we look at the popular benchmarking platforms like OpenLLM Leaderboard, they're simply averaging the multiple criteria values, giving all of them an equal weight to result in one single score, which is used to rank the LLMs. However, we do not see any correlation analysis between the different criteria, as correlation analysis can bias the results towards the correlated metrics. So we claim that LLM ranking is a process that is dependent on particular use case objectives. So the decision makers should actually have the opportunity to influence the process, namely specify their own preferences on the different criteria. So in this work, we combine theory from two different fields, the robust benchmarking and multi-criteria decision-making process. The robust benchmarking starts with selecting of a problem portfolio or a data set, then choosing complementary algorithms, in our case, large language models, ensuring fair experimental design, selecting performance metrics, and finally conducting robust analysis. In our case, we're interested in LLM ranking, which should result in selection of appropriate LLM. So we're interested only in the last step of the benchmarking process, assuming in this work that all of the previous steps are done in a robust manner by the benchmarking platforms as we reuse their data. In order to solve the LLM ranking problem, we're using theory from multi-criteria decision making. So some of the steps overlap, but what is important for solving our problem is that this field offers a different method to select weights for the different criteria based on their importance, and to select an aggregation method on how to combine the criteria into a single score. So there are a lot of different methodologies proposed. And finally, the process should end with sensitivity analysis in order to analyze how robust are the rankings actually on the changes in parameters, which is also very important. Our contribution is that we try to formulate the LLM ranking problem as a multi-criteria decision-making problem and to solve it through established best practices from that field. We performed thorough analysis of the potential of one method in order to limit the scope of the paper, Promethe 2, using an empirical approach and data coming from two of the most popular benchmarking platforms today, OpenLLM Leaderboard from Hugging Face and the holistic evaluation of language models, or HELM Classic Leaderboard from the Center of Research on Foundation Models at Stanford University. With this work, we demonstrate how a decision maker can robustly incorporate multiple performance and non-performance criteria in the LLM ranking process, how to select an unbiased set of criteria based on correlation analysis, and how to make the whole process more interpretable and transparent to the end user, because these algorithms are often perceived as rather complex for the end users. With this method allows a straightforward integration into any existing LLM benchmarking platform. As a summary, the research questions we try to answer: how can the Promethe method be used for LLM ranking based on multiple performance and non-performance potentially conflicting criteria? Then, how robust are the LLM rankings to changes in the algorithm parameters? And how can the decision-making process with this method be made more interpretable to the decision makers? Brief explanation of the methods that we use. It starts with definition, with creation of matrix consisting of performance, all performance or non-performance criteria that we will use to evaluate the alternatives. And the alternatives in our case are the large language models. So after the matrix is created, the next step is to calculate the pairwise distances by criteria for each criteria separately. So now we get the separate matrix of pairwise distances for each different criteria. In the third step, the decision maker actually gets the chance to specify the preferences over the criteria and the differences between the performance of different LLMs, namely whether he wants to emphasize even more the larger differences, to neglect some differences. And that is all possible through the different performance preference functions, which can be specified for each of the different criteria. Then all these matrices have to be averaged in the average preference index. Here, the decision maker actually gets the option to specify weights or his preferences over the different criteria, give a higher weight to a criteria that is more relevant to the specific use case. So finally, as given with the equations, the positive and negative preference flow are calculated for each LLM separately from the average preference index, and the net flow finally is the difference between the positive and negative preference flow to get one final score for each LLM that is used to rank the LLMs in the same order. In our experiments, we used three generalized preference functions: the usual preference functions that maps negative score to 0 and all positive scores to 1. Then the linear preference function that does the linear mapping between two thresholds. One that specifies if the difference should be neglecting or the indifference threshold. And the second one that specified that particular differences are very important and should be further emphasized through a score of 1. And finally, the Gaussian preference function that gives emphasizes to the larger differences between the language models. As weighting methods, we usually assign in our experiments equal weights, but in some we are selecting, for example, bias-related metrics to give them higher weighting, higher weights, but I will explain that on the later slides. We start with criteria correlation analysis based on the Pearson correlation coefficient between criteria pairs and do sampling of one criteria from each cluster of correlated metrics. Finally, we enter with sensitivity analysis when we calculate the Spearman rank correlation between all ranking to see if the method results are actually robust. Here I have a lot of details about the data that we used. Just briefly, we defined two types of experiments. In the first one, that is based on OpenLLM leaderboard data, we use multiple benchmark dataset and one performance metric for each dataset. We have 6 datasets in that platform. The metrics are mutually comparable as they are normalized by Hugging Face. But we also include in our experiments non-performance criteria, the parameter size, and the carbon dioxide emission. We create a subsample of the top 1,000 ranked LLMs based on the average score calculated by Hugging Face. and we have no missing values there. So we used the whole data set. The situation was a bit more complex with the Helm leaderboard, where we had a lot of missing data. So we only select 3 data sets to analyze. And in the Helm dataset, we have multiple performance metrics calculated for each data set. Namely, not just the F1 score, but F1 score related to fairness, using various perturbations of the words. F1 related to robustness, then fraction of toxic outputs, several metrics related to bias, such as stereotypical association related to gender and professions, and potentially uneven representation of different racial and gender groups in the data set. So here we had to handle even this reduced data set. We still had to do a missing value, select a missing value strategy. We decided for listwise deletion and selected 40 of the 49 LLMs for our analysis. So the data set that I mentioned are summarized here. So the first 6 are within the OpenLLM leaderboards, and the last 2 are from Helm, of which the last one comes into 2 versions. One when in the open book version and the closed book version, depending on whether asking the question, the source of the right answer is provided or not. So these are the scenarios created from the OpenLLM leaderboard. In the first 3, we are just changing, using all 6 performance metrics, just changing the reference function and using assigning equal weights to all criteria. In the 4th scenarios, we prioritize datasets with minimal contamination. As specified here, we use information from the authors of the leaderboard, which datasets are those, and applying Gaussian preference function to those to give them a priority over the rest. In the next 3 experiments, we again use the usual linear and Gaussian preference function, but now we experiment with assigning different weights to the dataset. Instead of prioritizing them through the Gaussian preference function, we now prioritize them through higher weights. And in the 6th and 7th experiments, in addition to the 6 performance metric, we now add the parameter size as additional metric. And in the 7th experiment, the carbon dioxide emission data that is also available in the platform. So we prioritize that last parameter through the Gaussian preference function. From the Helm data, we define similar experiments. So the first 3 just changing the reference function, and then we are experimenting, as I will show later. Here we have a correlated metric, a cluster of correlated metrics. So we experiment by sampling only one metric from the cluster, how that would impact the results. And finally, in the last experiments, we prioritize bias-related metric through Gaussian preference function and assign linear to the rest. So the results, first we can see the correlation between the different criteria on the first image for the OpenLLM leaderboard, and for the second for the Helm. For the Helm, we identified one cluster of highly correlated metric because their correlation goes above 0.9. The F1 fairness, and F1 related to robustness. While for the other data set, we do not have such a cluster. This is just to illustrate how different preference functions actually map the value. First one, the usual preference function, maps them to 0 and 1. The linear preference function and the Gaussian preference function, which emphasizes the larger differences. And about the results. So here we can see the top 10 ranked LLMs from each scenario. And the first column gives the average ranking, which is available in the OpenLLM leaderboard. So what we can conclude here is that only the first few large language models remain the same ranking with our experiments. However, there are cases like, for example, the 5th, 6th, 7th. They're highly ranked with the average score. However, when we apply our experiment, this new method for ranking, their rankings significantly worsen. Is worse. So, and most of them actually have very high number of parameters and high carbon dioxide emission. As we can see, they're performing very bad under the last two scenarios. The situation is similar here. Only few LLMs remain stable in their ranking across the experiments. So here we can see one cluster in the middle, while for the other, the ranking actually changes with the different experiments. For some, when removing the correlated metrics, they have better ranking with correlated metrics, but then this gets worse when correlated metrics are removed. So this for Helm are separate visualizations for each of the three data sets. In Helm, we do not have some average ranking based on which all LLMs are ranked. So I will just describe the sensitivity analysis. So this is the Spearman correlation between all different experiments. And here we can see that, for example, on the first picture, we can see that the rankings with the Promethe method are actually rather stable in experiments from 1 to 5, 3. So the ranking does not change, but that differs from the ranking which is available, average ranking, which is available in the OpenLLM leaderboard. As expected, when adding parameter which is non-performance, like parameter size or carbon dioxide emission, the ranking slightly change. But also, so those are less correlated, the least correlated with the average-based ranking. The situation is similar for the other three cases. Namely, we can see that the Promethe rankings have high correlation, particularly when the correlated metrics are eliminated from the data set. Finally, regarding the three questions, the first question, how can Promethe use for the purpose? So we actually applied the method on data from two benchmarking platforms, integrated decision makers' preferences on two different levels through the preference functions and through the criteria weights. And we use different types of visualizations. So we soon plan to publish this paper maybe on arXiv first and then submit it in some journal, and we will publish the source code together with the paper. So there are a lot of different visualizations which I did not mention, just to make the process actually more transparent to the end users. So how robust are the LLM rankings? So changes in preference functions do not change the ranking significantly, but filtering correlated criteria does so compared to scenarios containing such criteria. And adding new criteria slightly changes our ranking, but since the correlation is still high. So how can Prometheus 2 method be made interpretable to decision makers? The rankings are actually traceable by visualizing and outputting the average preference indexes, the positive and negative preference flow. They provide sufficient information on how the decision making process actually goes. And through visualization methods, we saw that they, like the dendrograms or heat maps, they clearly separate good alternatives from bad ones. As a conclusion, we believe that LLM ranking is a problem that is dependent on the specific use case and is usually based on combination of both performance and non-performance, often conflicting criteria. Multi-criteria decision making field offers a lot of methods to solve these problems. In this work, we analyzed only one, but we hope to motivate analysis of different and comparison of different methods in the future, because they provide flexibility and robustness of the LLM rankings, and the proposed LLM ranking process can be integrated into any platform and made interpretable to visualization methods. Thank you.
Questions, discussions?
One practical question. Let's say you have done this analysis, there's correlation between different metrics, etc. Can we say that the ranking of the models there is something else, or how I can choose which is the best? Can I trust this that the Hugging Face has?
Yes, I understand. There are a lot of different methods that can be used. You cannot say which one is best, but I think that this type of approach is probably better from simple averaging overall performance criteria. However, yes, that is correct. We selected Prometheus method because it allowed the decision maker to incorporate different preferences at several places in the process. Other methods are not that flexible. But yes, probably even more sensitivity analysis are needed to see how even slight changes, for example, in the parameters of preference function change the ranking. But if the ranking stays stable, they're probably, I don't know, they can be trusted, for example.
In that direction, maybe,
You can see something.
Yeah, my point is, for example, now the difference is different LLMs in the last couple of months really small. So there, someone is 62.2, the model is 62%. So how this will change, for example? Because from my perspective as user, it's quite the same. So probably this approach can give me more information what to do in that.
Well, yes, probably the differences would be emphasized if larger number of criteria are involved. If the decision can be made on one or two criteria, then we can probably use just the results in the benchmarking platforms. But when, I don't know, when we have to combine, if we want an LLM that performs well on a large set of tasks, I don't know, 10 or more, then probably there would be some differences there on different types of machine learning problem, I think.
This was a discussion.
Yes.
Can I just add to this? How is context dependency captured by these?
Context dependency is captured by actually giving the decision maker, the user, a chance to specify the preference function and the weights over the criteria. Now here the problem is that the user may not know how to weigh the different criteria, but there are also methods or algorithms that can be used for that purpose, which can be used in combination with any of those methods, like entropy-based, which Tome has used a lot, then based on standard deviation. And but that is the actually the context is integrated in that way. And through the different reference functions here, the threshold, for example, on the linear function can specify in which range we want to look at the differences and which can be neglected, which can be emphasized even further. So in these 2 points, we can integrate the context of the use case.
Sounds like this can also contribute to better explainability, adding information. How can this be actually practically?
We are publishing our code on GitHub. So we are giving the opportunity just to use it with any data set. So we can just upload, use it with any tabular data set and get all these visualizations on how to just run the code. And get visualizations for each step of the process, all these large matrices. I have some examples. And for each step of the process, you can get, I think, in my opinion, sufficient explanation how things actually go in each step. But you still have to have some knowledge in this area. This is not for just an ordinary user.
I have a question. As far as I understand, you're using a black box evaluation for the large language model. Basically, you're using the performance of the large language model on a given task or on a given data set. My question is, are you planning to include some of the internal features of the large language model that have maybe some aggregated information about the attendance matrices inside them, or maybe the Vim search information in the decision-making process for those models that were available in order to get better explainability or better features, not only the black box features, but some of the internal features or some of the internal matters that are going inside the model. So basically, given a prompt, we can see for which prompts which things are activated, and then decide whether this answer is acceptable or not, and then use those internal things in order to cluster, or in some of the approaches Tome mentioned earlier, to provide better features in order to cluster them and use some of those methods for better describing the landscape of the large language models.
Yes, that is actually the purpose of the project AutoLLM-Select. There we plan to go into very much details to use the actual prompts and the results that the LLMs got on each separate sample to create different types of meta features and to use them to predict the performance. So we will actually go into much more details there.
This
is just yes.
Maybe I can just set a comment. So this is only the performance space. And if you think about what I presented, I always said we have problem portfolio, algorithm portfolio, and then these trajectories, right? What Anna is presenting is only the performance space once the data is collected. So if you think about this, in my presentation, it will be performance to like algorithm features, only at the end, then the result, right?
Yeah.
But what Anna said, actually her proposal is exactly like what Rista you said, for which prompts of the it works, why it works, and all this with sentence embeddings and
Also, not only the prompt, but also we can analyze the activation function functions inside,
everything.
and we can say, okay, for this class of prompts, we go through this path, some kind of like graph, maybe some information or activation information as a matrix.
No,
kind
no,
of like
it's clear what you said, because what we have done in optimization is when you do vision model and you're trying like a computer vision model on ImageNet, right? And then you're looking for the best architecture of Alex or whatever, like network at that time. Then we said, okay, based on how actually the backpropagation derivative is changing, you can extract these trajectory features, and you can say like training this machine learning model on this data set is similar like solving Rosenberg function with covariance matrix adaptation. So all these like variables are taken into account. So this is what I said, like what Anna said, this is only the performance phase, right? We said, okay, we have all of them. Now we will have like all these promptings and everything. Today, like in the morning, we got like from ICLR 2025 for one workshop from Wyden. They sent us a lot of already calculated features, like for the prompts with different embeddings, performance metrics. So now we have the problem portfolio, the features, everything, which came to us in a really nice JSON structure. So actually we can do a lot of things. But also Anna is doing a lot of work like on the problem portfolio side. When you think about data set, prompts, different metrics.
Okay, do we have other discussion?
Thanks. We are waiting.
Yeah.
Okay, so thanks again for your presentation, and also Tome for sharing your work with us and the progress, and I hope that we will inspire other people to join you in this journey in search of better algorithms for the data sets that you have. So I would like to thank you all for attending this session today, and to wish you, for all of you present over here, to have nice social part of the conference tonight.
Maybe one more thing.
Yeah.
There was a panel which was planned, but we are out of time. So if you have questions about data privacy and trustworthiness, here with you from GSI. Also, like you can ask everything about AutoML binds part algorithms. I'm pretty much sure she knows even better than me because I'm just using them to collect data. So if you want, like you can talk also a lot with on these topics. So
We will talk.
Yeah.
Let's.
Sure.
And
Thank you everyone for
Thank you.